All right, good morning. Happy Wednesday. I hope your day has been going well. I sure liked your presentations on Monday. They were really, really cool. We are going to watch Prasant's presentation today and stuff. There were some tech issues going on, no big deal. But I do want to talk about what's happening in the final week of Chem 223, which is just crazy. And so today, if you got it, turn in problem set 6. Get a copy of Take Home Quiz 6 and Take Home Seminar Self Quiz 6. Those will both be due Friday by 9 a.m. You can turn them in early if you want, or in my mailbox, or you can bring them on lecture on Friday, either way. Monday morning, next Monday, the lab final will be released. It'll be something that you should print and complete. You'll turn that in to the final time we'll meet. Next week, the only time we'll meet is next week, Wednesday, a week from today, 8:45 a.m., this room, AC 1303. And when you're here, you'll turn in the lab final. You'll also turn in the last lab, the organic chemistry lab. You'll take the lecture final. You'll be done by 10:45. We're getting down to the end. Any questions on that kind of stuff? Okay, without further ado then, let's change over to Prashant. So yeah, do your thing, man.
Hi everyone, my name is Prashant, and I do a presentation on the heart. Okay, so the heart is located basically in the medial left portion of the chest. Its primary function is supply oxygen to the rest of the body. So all tissue require oxygen. Without it, they end up dying, and the heart does that. So the heart is composed of 4 chambers: the left and the right atrium, and then the left and right ventricles. It also has valves that prevent regurgitation of blood, so that deoxygenated and oxygenated blood do not mix. All these structures play an important role in unidirectional blood flow, meaning it flows in one direction, and it is very good at pumping to the rest of the body. Okay, so it says blood flow from body, heart, lungs, etc. So this is like the basic, kind of the simple version of what blood flow looks like. Blood flow, as you guys probably already may know, veins transport blood to the heart, and arteries transport blood to the rest of the body. So the blood is received by the right atrium, by the superior and inferior vena cava. And then it is transferred from the right atrium to the right ventricles, which is then pushed into the lungs, where oxygen exchange happens. So the CO2 is taken out and oxygen is added into the blood, and then it's sent to the right side or left side of the heart, where it's pumped to the rest of the body. So for this to happen, there's multiple factors. The main one is conduction. Conduction of the heart is very complicated, but I simplified it to SA node to SA node to AV node to the ventricles. Just that area of the heart can take hours to talk about, so I simplified it to that. This talks about systole and diastole, which just means one is contracting while the other is relaxing. This is important because the heart needs to relax to get the full volume of blood, so that it can pump adequately to the rest of the body. This also talks about how the heart alters its function depending on supply and demand. So if you're running a lot, you're gonna be pumping a lot more, and when you're at rest, you're gonna be pumping a lot less because you're used to that, basically that environment where you're running a lot. So this talks about the conduction a lot more. So for conduction to happen, you need a concentration gradient, meaning there needs to be difference in ions intracellularly and extracellularly. If there's too much outside or inside the cell, it causes conduction issues, which can be very deadly. That's why it is important to monitor lab values to make sure everything is okay. So yeah, this talks about SA node to AV node and ventricles. That's basically the consensus of how electricity travels within the body. Why is this important? So as a nurse, there's a lot of factors that have to determine and understand, so you can communicate with the providers and the rest of the care team. If you don't know the normal function, you don't know the abnormalities of the heart, So that's why it's important to understand. Things like heart rate and blood pressure are parameters to whether you can give medications or not. So it is important to realize what is a normal heart rate, what is a normal blood pressure, what can be scary and what is not scary. For the most part, people who aren't symptomatic of having low blood pressure or low heart rate, if they're not asymptomatic, then it is not as scary as if they are symptomatic. So I talked about a lot of the normal function of the heart. There are abnormal functions like heart failure or conduction issues like AFib or ventricular fibrillation, where the heart isn't conducting electricity as well, and that can be very scary. So it's important to realize what is a normal ECG or EKG, what are normal telemetry reads for that reason. And that's pretty much my presentation. Thank you guys so much. You guys have any questions at all?
Can you explain to me which artery gets pumped through the oxygen to grab the oxygen to be pumped to the rest of the body?
So the pulmonary artery is what is used for deoxygenated blood to go into the lungs.
Okay.
And then capillaries transfer, I guess gas exchange happens, and then it's transferred back to the heart. And then the left ventricle eventually pumps out to the rest of the body.
Gotcha.
Yeah.
All right. Nice job. Well done, man. Yeah. All right. Well, now back to your regularly scheduled programming. So, I'll close that window. So first of all, welcome. Good to have you here. We're down to the final week of Chem 223. So just a FYI, down here, and if you want to come down here, problem set 6. I've got a pile going. Also grab a copy of Seminar, Self-Quiz 6, and Quiz 6. Those will both be due Friday morning at 9 a.m. You can turn them into my mailbox or under my office door if you want earlier, but that's when they're going to be due. So we're getting down there. Monday morning, you're going to get an email from me with a link to the lab file. That's something you should print off and complete. That will be due Wednesday morning in this room, a week from today, at 8:45 a.m. And at that time, you will turn in the lab file, you'll turn in the organic chemistry lab, and you'll take the lecture final. So by next week, Wednesday, 10:45, done with Chem 223. Oh, yeah. Any questions on that? Okay. The lecture final will have 28 multiple choice questions. It's over everything from Chem 221 to Chem 223. Now, I've already talked to several of you about this. I know that's a lot of material. Please realize these aren't going to be super deep questions, all right? Some of the stuff we did, like, for example, with equilibrium or molality to mass percent, those kind of things might be pretty deep for the lecture final. So they're going to be more broad kind of questions. All of that stuff is up here, all right? So you just need to dust it off, kind of prepare it, and you'll be good to go. And people have usually done really well on the lecture final. 28 multiple choice questions. Make sure you bring your calculator, bring something to write with, and as I said earlier, the organic chemistry lab will be due, and the lab final will be due. If you don't have these ready to go, your score will be a 0, so bring them along. All right, there's no turning them in late or something like that. The lab final, which you'll get on Monday, will have 5 short answer questions, all right, over the different labs we've done. You can use your old labs to work on it, but you can't talk to your lab partners and your friends at MIT, stuff like that. So it will be something you do by yourself, but you can use the old labs. Show your work, all that kind of jazz, should be pretty chill. We're just about there. Questions, anything like that? Okay. If you do have any questions, you know how to get a hold of me, so I encourage you to let me know. But we are just about done. The light's at the end of the tunnel, so let's make this happen. What we're going to do with the rest of the time, both today and Friday, is I'm just going to review some stuff primarily from Chem 221 and Chem 222. So just to kind of give you a heads up of the kinds of questions you might see, hopefully this will also kind of like help to dust off that material from previous courses that you have seen before, you just haven't thought about very much. So, All right. Questions? So this is the question back from Chem 221, and it says, which statement would be used here to describe the composition of a neutral iron 58 atom? All right. So think about what it means to have iron. Think what it means to have that 58. We'll talk about that here in just a little bit. Okay. So the periodic table has these big blue numbers that organize all the different atoms. And for iron, Fe right there, you can see the number is 26. What does the 26 represent? Protons, yeah, absolutely. So iron, regardless of what number follows it, always is going to have 26 protons. Now, if it's neutral, the positive protons and the negative electrons will be equal to each other. So a neutral atom would have not just 26 protons, but would actually have 26 electrons as well. So the only thing then we don't have is the neutrons. This number is called the mass number. It's equal to protons plus neutrons. So if you take 58 and subtract the 26 from it, that'll give you the number of neutrons. And that comes out to be answer B. So the iron number, the name itself will tell you the atomic number, and the atomic number will tell you the number of protons. And a neutral atom will have equal protons and electrons. Mass number, that number equals protons plus neutrons. Questions? All right. Here's a compound. It's got only nitrogen and oxygen. And this compound is found to be 46.67% nitrogen. So the question is here, what is the empirical formula? Now, almost always percentages in chemistry are mass-based percentages, all right, so grams. So see if you can use that information to calculate what the empirical formula of this compound will be. Good old H2O. Does H2O mean 2 grams of hydrogen for every 1 gram of oxygen, or 2 moles of hydrogen for every 1 mole of oxygen?
Moles.
Moles, you bet. Chemists love the moles. Always guess the moles if you have to. So formulas like this, and all of these are mole-based formulas. So 46.67% is relationship to Gesundheit, to the grams, all right? So what I would do on this problem, I would turn this into grams, 46.67 grams of nitrogen. 100 minus this number will tell you the grams of oxygen, all right? So 100 minus 46.67 would be the grams of oxygen. Then you want to turn both of those numbers into moles. So for nitrogen, you would divide by 14.01 or so. For oxygen, you divide by 16.00. You're going to get the mole values of N and O. You can compare them. If you do all that, here's the math. It comes out to be about 3.3 moles of oxygen, about 3.3 moles of nitrogen. Divide both of them by the smaller number. Comes out to be NO. All right. So percentages are mass-based grams, grams to moles using molar mass. You can then compare the moles to get the empirical formula. Cool. Any questions on that? This is a question where we've got nitrogen and hydrogen making ammonia. And we've got 10 moles of nitrogen and 25 moles of hydrogen. And the question is, how many moles of ammonia, NH3, are we going to make? So see if you can figure this out. I'll talk about it here. So just like the formula H2O is a mole-based formula, a balanced equation like this one is also a mole-based relationship. So it says that 1 mole of N2 is needed for 3 moles of H2, and you'll make 2 moles of NH3 in the process. So what we talked about then is you can have relationships based on these different things. So you could write 1 mole of N2 for every 2 moles NH3. And of course, like anything, you could flip them. You could write it 2 moles NH3 for every 1 mole of N2. And of course, you could do it for H2 and all that kind of jazz too. So in this question, if you start, for example, with 10 moles of N2, you can multiply it by one of these factors from the equation. The moles of N2 will cancel. You'll have just moles of NH3. So 10 times 2, it looks from here like it would be about 20 moles of NH3, which are possible. However, which is really cool, a lot of you saw it. This is an example of a question where you have two reactant amounts. And this kind of problem is a limiting reactant problem. You don't know for sure which of the reactants, N2 or H2, is going to create less product. Now, just looking at the numbers of reactant, 10 versus 25, it seems almost silly to even think about the 25, because 25 moles is a lot bigger than 10 moles. However, if you do this, here's what it would look like. 25 moles of H2. There are 3 moles of H2 for every 2 moles NH3. Well, 25 times 2/3 comes out to be a number which is smaller than 20 moles of NH3. It comes out to be 16.7 moles. So what this tells the chemist is this is not enough H2 to use up all the N2, all right? H2 is the limiting reactant. It's going to prevent you from making all the NH3 you could based on the other reactant. So several things about this problem are kind of important. First of all, just realize a balanced reaction gives you all kinds of conversion factors, and they're all mole-based, so if you have to turn grams into moles first, that's cool. Second of all, you may see a problem where you have two reactant amounts. Here they're both moles, but they could be grams or milliliters if you had molarity, whatever. Make sure that you check both reactant amounts, or 3 if there's 3. And the smallest one is going to be the moneymaker, all right? This reaction could only make 16.7 moles of NH3. So if you told your boss, for example, you could make 20 moles, I don't think so. You don't have enough H2. H2 is limiting how much NH3 you can make relative to the N2. Any questions on that? Here's a question that kind of is a little bit of Chem 221 and a little bit of Chem 223 as well. And it says, which of these compounds would conduct electricity in a water-based solution best? All right? All of them will conduct a little bit, but one of them is going to conduct far more than the other ones will. So see if you can tell me which one that's going to be. I wrote 8 chemicals up here on the blackboard. What are those 8 chemicals? What do they represent? Strong acids and strong bases. Outstanding. These are really important to chemists, all right? Not only do they give a lot of energy, but the conjugates don't have any effect on pH, blah, blah, blah. And for this problem, what's really important is that all of these dissociate 100% into their ions. So for example, up in Longview, Washington, they had a bunch of sodium hydroxide go in the water. Anyway, they were worried about it, and I think they should still be a little worried about it, because all of that NaOH goes into Na plus and OH minus, all right? None of it stays as molecular NaOH. So that means you're gonna have a big pH effect on the Port Columbia, et cetera, et cetera. However, for this problem, what's important is that HBr, you can see, is on this list. and none of these other ones are. And a strong acid dissociates 100% into positives and negatives. So you bet it will conduct electricity better than the other ones. These other ones will break up. Like these are acids, that's a base, this is an acid. They will conduct, but they won't conduct to the same amount. So like 1 mole of HIO, I think I read the other day, it's like 1 in 10 million. It's really a small amount of molecules that break up. So you put electricity through, and some will go from one side to the other, but you don't have as many H pluses and IO minuses as you would H pluses and Br minuses in a strong acid. So those strong acids will just get the electrons transferred over easier. They'll conduct electricity better. And if nothing else, just remember, I keep hitting you over the head, I know, with this list of 8 things. If there's ever a question like this, probably one of these 8 will be the answer. Any questions? Okay, so here's a question, and it says, which of these equations represents the balanced net ionic reaction or equation for the reaction of potassium hydroxide and iron 2 chloride to give iron 2 hydroxide and potassium chloride? So see if you can figure out which of those up there would be the best representation for this problem. And note again, it's a net ionic equation. Okay. Potassium, group 1A, positive 1. Hydroxide, a polyatomic ion, OH minus. So when they come together, KOH will be the formula for potassium hydroxide. Iron 2 means you've got a Fe plus 2. Chloride, like always, is minus 1. So when you put those together, FeCl2. This is a double displacement reaction. The metals will trade places with each other, but it tells you up here too what's going to happen. The iron 2 goes with the hydroxide. Iron is plus 2 here. It'll be plus 2 down there, but hydroxide is still minus 1. So FeOH2. And the other species, potassium chloride, K plus and Cl minus, KCl. Questions on that? Anything with K, always AQ. Anything with K plus, Na plus, Li plus, as well as nitrate, those kind of things, always AQ. The ones we don't know here in terms of solubility would be the FeCl2 and the FeOH2. But group 1A cations lab, silver, lead, and mercury, they are always insoluble with chloride, but almost everything else is soluble. So iron is not silver, lead, or mercury. That means this is going to be AQ. Anything with chloride, bromide, or iodide that's not silver, lead, and mercury, AQ. The only thing we don't know is this one. You could look this up on a table, or I'll just tell you this one's going to be a solid. Most hydroxides are insoluble unless they're with sodium, potassium, lithium. Let's balance it. We'll put 2's right there. This is the balanced molecular equation. Okay? Questions on that? All right. Net ionic means pull all the spectators out. Spectators are ions that are in aqueous parts on both sides. So you can probably tell maybe from there. But in case you don't remember, which is cool, to write the net ionic equation, you break up everything that's AQ. So this would be 2K plus and 2OH minus, because KOH is AQ. This would be Fe2 plus and 2Cl minus, because it's AQ. But you never break up solids, liquids, and gases. Leave this as FeOH2 solid, but we will break up the KCl into 2K plus and 2Cl minus. The spectator ions are ions on both sides of the equation. So chloride here is a spectator, potassiums are spectators, but you don't cancel the hydroxides and the iron 2 plus with this one right here. They're different species. So what it comes down to is 2OH minus and Fe2 plus makes FeOH2 solid. Answer C. Okay. Again, you might be able to just see that, K and Cl are both in aqueous things, so that gets them out of there. Most of the negative polyatomic ions are insoluble, unless they're with sodium, potassium, stuff like that. Any questions? Concentration in chemistry is almost always molarity, big M. And what I have here is a problem where you've got sodium carbonate. Here's the molar mass of it, by the way. You're putting 6.73 grams of it in 250 milliliters of solution. Can you tell me which of those is the concentration or the molarity of your sodium carbonate solution? Work on it a little bit, and we'll talk about it in just a second. All right. So big M stands for moles over liters, okay? So in this problem, what you need to do is take the grams of sodium carbonate, divide it by the molar mass. So grams divided by grams per mole will give you moles, the top part. And the bottom part, you need to turn the milliliters into liters. How many milliliters in a liter? 1,000, thank you. So 250 divided by 1,000 will give you the liters. 0.254 moles per liter. They'll refer to this as molarity, concentration. If you see something in square brackets, that's another way of saying it's moles per liter. So, cool. Any questions on that? Oxidation numbers help you to see where electrons are going to and coming from. And KMnO4 has a manganese in the middle. Now, manganese is a transition metal. Its charge is all over the place. But what I'd like you to do is basically tell me what the charge is on the manganese, all right? Metals are usually positive, but see if you can figure out what the charge will be. We'll talk about it in a second. Fantastic. In a problem like this, K plus, Na plus, Li plus, all the group 1As, usually positive one, and that very seldom changes. If you see oxygen or hydrogen, the oxygens are usually -2, the hydrogens are usually +1. So in this case, you've got 4 -2 oxygens, -8. Your potassium is +1. So -8 and +1, you can see there's like a difference of +7. And since the whole molecule is neutral, there's no positive or negative. That +7 is what the charge is going to be on your manganese. So they've referred to that as the oxidation number of your manganese. It's missing quite a few electrons. You can set this into like an equation, like you have +1 from the potassium. Who knows what manganese is, but you have 4 times -2 from the 4 oxygens. And since KMnO4 is neutral, all of that equals 0. If it would be +1, then you'd set it equal to positive. I heard it by Crook. Question? Sweet. Enthalpy. This is a problem where silane, SiH4, reacts with oxygen. It makes SiO2 and water. What is the delta H of this reaction, the enthalpy of this reaction? So see if you can figure it out. Those are all the values you need for this particular problem. We'll talk about it here in just a little bit. Okay, so enthalpy is the delta H term of thermodynamics. And if you have a problem like this, most of these will be delta H of the products minus delta H of the reactants. So you take the SiO2 and the 2 waters and subtract the SiH4 and the 2 oxygens. Now, notice I said 2 waters. Each of the values in these tables, they're almost always per 1 mole. So for the water here, you'd want to take this number and multiply it by 2, all right? Because that's where the 2 part there comes in. You'll also see there's no oxygen. The elements in their standard states have values equal to 0. So that's why it's not listed. So honestly, if you see a problem like this, you're like, hey, where's that value? Probably 0, all right? Oxygen is an element. Sodium metal would be another one that'd be 0. Neon gas, bromine liquid. Anything, all the elements in their normal states would have values equal to 0. So mathematically, you take the SiO2, this number, you would add it to 2 times this number, and then you would subtract the reactants, oxygen 0, and this is the only reactant with a delta H value. So it would be like minus 34.3, basically. If you got answer B, minus 1428.8, booyah. Here's the math. You can see the SiO2, the 2 waters, you're subtracting the SiH4, and the oxygen is just 0. So, questions, any of that? This process works really well for Gibbs free energy. It's also delta G products minus delta G reactants. The elements will be equal to 0 for that. Entropy values will also be delta S of the products minus S of the reactants, but all the elements up there will have non-zero values. So there would be a value for oxygen on those kinds. So, okay. Now, the alkali metals are group 1A, and all of them have kind of a generic valence electron configuration. So valence means the outside atoms. See if you can figure out which of these generic representations would best represent the alkali metals. We'll talk about it here in a little bit. Remember, valence are outside electrons. Sweet. All right, so earlier we saw how an element has an atomic number. In sodium's case, it's number 11, iron was number 26. Officially, the atomic number goes down there, whatever. Anyway, in this problem, that's going to equal the number of electrons. If it's a neutral atom, protons and electrons equal each other. So we need to distribute the 11 electrons of sodium, an alkali metal. You always start off with 1s2, 2s2, 2p6, 3s1 would be the electron configuration. And if you count the superscripts, 2 plus 2 plus 6 is 10 plus 1, it should equal that number right there, et cetera, et cetera. However, in this problem, we want to know like what a generic representation would be. And in chem, when we did the valence structures, the Lewis structures, group number represented the valence electrons. So all of the group 1As were 1 electron. And where that comes from is that all of these are core electrons. The lower ends are deeper in the core, and the higher ends, the number in front of the letter, the higher ends are more outside. So in Chem 221, we would refer to this sometimes as neon 3s1, all right? That was the kind of quick and dirty representation of it. Well, sure enough, if you go, for example, to potassium, potassium is argon 4s1, and lithium, as an example, would be helium 2s1. So notice that all of these alkali metals, they've got one valence electrons in this outer s shell. And the number there represents what group the element's in. So sodium's in period 3, periods go left to right. So that's why it's 3s1. Potassium, the next one down, is in the 4th period, so it's 4s1. So the generic representation then would be just ns1. That outer electron is going to be in the group number of the alkali metals. So francium would be 7, for example. It would be 7s1 for francium, and it would have a core of the previous noble gas. Honestly, most of the time we don't care about that. The valence electrons are usually the active ones in this one. So ns1 would be the alkali metals, ns2 would be alkaline earth metals, ns2np5 is usually seen for the halogens, group 7. Questions? And then finally for today, which of these elements, Na, B, Al, and C, would have the largest atomic radius, the biggest size? See if you remember the periodic trends, and you can see which of those would be the biggest. So when it comes to size on the periodic table, if this is a generic representation, hydrogen would be upper left, helium upper right, francium lower left, and radon or OG lower right. Sizes get bigger as you go left and down. So pick the element which is most left and down on the periodic table. So carbon is most up and to the right. Going left, you get to boron. Below boron is aluminum. And definitely lowest and on the left would be sodium. So sodium would be the one with the biggest size. Now these sizes are opposite the other types of things. For example, electronegativity. So I'll just show you the answer to this one. For these ones, you want to go up and to the right to figure out which would be the largest. So electronegativity as well as electron affinity, those kind of things are up and to the right. Oh yeah. Questions anyways? All right, thank you for being here. Grab copies of the take-home quizzes and turn in Prop 6 if you haven't done so already. Have a great day. I'll see you later.